Okay, so we're looking at the simplex method, and I just want to talk to you about some of the kind of conceptual background that's going on here, because they're not just going to expect you to be able to perform the simplex algorithm, they're going to expect you to be able to interpret things that are going on, which is why we're really going to try and understand everything that's happening, as I always do with stuff in decision. I don't want to just tell you do this, do this, do this. I want to really tell you why these things are working, because if I can get you to do that, you can reach those A-star marks way, way more easily. So there are a few conceptual points to explore before we look at the algorithm in detail. As part of the simplex algorithm, we choose a variable in the objective function to increase in order to increase the overall function that we've got there. Firstly, let's consider the logic for selecting which variable we should increase in order to increase the overall objective function as quickly as possible. So let's consider the following objective functions that I've got down here. And what I want you to do is to pause the video and think to yourself, which of the decision variables would you choose to increase in order to have the biggest impact on increasing the objective function? So pause the video, think about these 6 different objective functions that we've got here, and think, would you pick X, Y, or Z to increase to try and increase the value of P as much as possible, as quickly as possible? Okay, so when we look at this first equation, which is that P is equal to 4x plus 2y, if I was going to try and make P get as big as possible, as quick as possible, I want to increase the value of x, because it's got a coefficient of 4, right? So the one that I'm going to want to pick for this one is I would want to increase the value of x. So the one that I'm going to, the decision variable that I'm going to increase is I would choose to increase x for this one. And now that I've said that, you can probably think about this one. Now, sometimes people might go, oh, well, the 6 is the biggest one, so I want to increase y. But careful, it has a negative in front of it. If you make y bigger, you're actually going to be decreasing the value of this whole function. So we don't want to increase y. I want to choose between x and z, but x has a higher coefficient. So I'm going to want to actually increase the value of x in this case to try and increase the value of the objective function as much as possible. And then in this last one that we've got here, I don't want to do anything to do with the negative 4z, because if I make z bigger, I'm going to actually be decreasing the value of p, because you'll be adding something more negative on. And here I've got 4x and 4y. I have some equality there, so it doesn't matter which one that you have. It would usually be sort of like told to you in the question which one you should do. Well, there's these 2 options that you've got. So you're going to actually, for this one, you will either be able to increase x or y. Now, I've written these ones down here because all of these ones that are on the bottom half of the page, these are what we would call like the standard form. The standard form is where we have just the constant on that side. A bit like what I'd mentioned at this space where we always just have the constant on the side for the constraint. We do the same thing for the objective function, and we push everything all on one side so the constant is just on the right-hand side. Now, thinking about this, because we've shifted these parts to the other side, here we were looking for the most positive ones. On this stage, we're going to be looking at the ones that are the most negative. So in this case, the one that we would want to increase is this part, because if this makes it more negative on this side, the value of p is actually going to be increasing, because this would be put onto the right-hand side. So in this case, I'm actually going to increase x. I'm going a little bit quicker for these last ones that we've got here. I've got a choice of the most negative one. The most negative one in this case is z, so I'm actually going to increase the value of z in this case. And then in the last one that we've got here, I have the most negative one. I'm going to increase y. Obviously, if I increased z, I would be decreasing the overall value of p. So I would like to increase y for this one. And so our general kind of pattern for this is when in standard form, increasing the most negative will increase p the most. And the reason that we try to do this is by doing that, it tends to minimize the number of iterations of the algorithm that we have to do. So the whole point of this is we're trying to do it as quickly as possible, so it feels sensible that we're going to try and pick the variable that will help us get to the solution as quickly as possible. It's all about trying to sort of do things as efficiently as possible here. The second conceptual thing that we want to do is to consider the significance of the slack variables on the graphical representation that we have. So I have a region that has been represented. This is the region that we're talking about, the feasible region, and it represents the following constraints. X plus y is less than or equal to 7. Well, there is x plus y being equal to 7, so obviously we're talking about everything that's underneath it because it's less than or equal to. We have 2x plus 3y is equal to 18, so we've got this line, and again it's less than or equal to 18, so it's underneath it. And we have those standard non-negativity constraints that x and y are both greater than or equal to 0, which is why these bits have been shaded, and we only have this white section that is left here. We'd probably normally label that R, but I think in the context of this part, I'm just going to keep the diagram looking as neat as we can do. And so what I want to do here is to rewrite the constraints using slack variables, and then I'm going to investigate the values of the 4 variables at the 4 vertices of the feasible region here, 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 and here. So first things first, we're going to use some slack variables. We're going to say x plus y plus r is equal to 7. I'm then going to have 2x plus 3y plus s. Sometimes I leave a gap so that there's like a column for r and a column for s. You'll see why I do that as we go through this exercise. And so I've got the slack variable for this one that we have here. Now, the easiest of these vertices to investigate is the first one that we know is a definite solution. And this one here, we know that x is equal to 0, and we know that y is equal to 0, because that point lies on the line x equals 0, and the line y equals 0. It's obviously the starting point that we've got. Now, if you think about this line x plus y equals 7 that we've got here, I know that if I have something that's underneath it, I still have some capacity, I still have some slack in the function. Whereas if I'm actually on the line here, so at this point, for example, it is 3 for y and 4 for x, there is no slack. The value of r in x plus y plus r equals 7 is 0. And it's the same here, that 5, 2, the value of r here is 0. 6, 1, the value of r is 0. The value of r is 0. So all along the line, the value of r is equal to 0. So let me just highlight this for a second in this green that we've got here. So I'm going to say all the way along this line, r equals 0. So I'm going to say r equals 0 along x plus y equals 7. And I'll highlight that in green so it's clear of what the things are that we're talking about. And then if I highlight this in a yellow color, you can kind of imagine what I'm going to be saying about this one. Everywhere along this line, the value of s is going to be equal to 0, because if you're in this region down here, but we actually wanted to get it onto the line, we would have to add something onto it. So I'm going to say that s is equal to 0, and that is along the line 2x plus 3y equals 18. And I'll highlight that in yellow to make that clear of what's going on. So now what I'm going to do is investigate what's going on at these other vertices. Well, this other vertex that we've got here, the thing that's true at this vertex is that we can see that the value of the value of s is equal to 0 because it's on the yellow line that we've got here. So the value of s is equal to 0, and we can clearly see it's also on the line that x is equal to 0, or the x coordinate is 0. So we have x is equal to 0 and s is equal to 0. And clearly you can also see that the value of y is 6, and we could work out the value of r as well, because it's going to also be equal to 1, because we've got 0 and we've got 6 for the x and y values. So the value of r to make it up to 7 is 1. So we do actually know the value of y is 6 and the value of r is 1, and that might come up later on when we're investigating some things. Now I'm going to look at this vertex that we've got down here. This you can probably imagine what it's going to be. So you can see that our y is 0, and actually it's on the green line, which is where r is equal to 0. So we have y is 0 and r is 0 for this one. And then our last vertex that we're going to consider is this one that we have here. And that's clearly where both r is equal to 0 and where s is equal to 0, because it's on both of those lines. And so we've got all four pairs that we have, okay? We've got four different variables. We've got the four different pairs that you could take from it. X and y, x and s, x and r. We don't have x and r. Now x and r, we don't have all the possible pairs. X and r being equal to 0 would be up here, but that's not inside the feasible region. This one over here would be y and s being equal to 0, but that is not inside the feasible region either. So this is why we've got a couple of them that don't feature, because they're not actually inside the feasible region. So what happens in this is the simplex method goes from vertex to vertex until the objective function can no longer be increased. What happens is it starts at a feasible part on the graph and it travels until it gets to one of the vertices. We have to make sure that we stop here and that we don't go all the way up to this one, because that one goes outside the region. And if we can make it better, we travel alongside here, and we have to stop here rather than making us travel all the way over to here because it's not inside the region. So in the next video, you're going to see me explore as we kind of move around this graph to get to the optimal region for this particular one that we're going to be looking at. So come back after this. We're going to do the algebraic and tableau methods, and this is where it gets kind of like a lot of concentration needs to be had. So get yourself ready for that. Okay, so we're going to look at the